Hello. Now that we are done with topic 0, as I call it, we are finally able to start with the actual material from Unit 1, which is Topic 1, which is mechanics. And we will start with Topic 1A, which is motion. I'm afraid the next couple of minutes will be a little bit boring because we will start with lots of definitions, okay? And here I'm working with two sets of nodes, so I will try to do my best to convey the meaning behind formulas and so on. So let's start by defining velocity and acceleration, okay? So let's start with that. Velocity and acceleration, okay? These are core concepts when we talk about motion, okay? So the first one we will define is actually speed, not even velocity. And speed is defined as distance over time, okay? It's measured in meters per second. And it's also expressed by d over t, okay? And this is actually a scalar quantity, okay? It doesn't have a direction like velocity does. It's just the magnitude. So let's write it here. So scalar. And what I mean by that is think of the speedometer in your parents' car, or maybe your car, because I don't know, year 13 students are, some of them are adults, so they might be able to drive. So anyway, think of a speedometer. So if the car is going with 60 kilometers per hour, that's the speed, because even when you turn, the speedometer still says 60 kilometers per hour. It doesn't take the direction into account, okay? So this is what speed is, okay? It's a scalar quantity, no direction, okay? So let's write that down. So speed, as in I show speed, I'm kidding. So speed is a scalar quantity with no associated direction. Okay, so that's done. There's nothing more to talk about. To calculate it, you need to measure the time to cover some distance, okay? Again, without taking the direction into account, okay? So that's it. Next, velocity. Velocity is given by displacement over time, also expressed as delta S over delta T, I'm sorry. And okay, let me squeeze this. Sorry, let me squeeze this to the left, so I can write over here that this is measured also in meters per second. All right, so now this is a vector quantity with an associated direction. Okay, and later I will have examples about how displacement is different than distance. But let me briefly mention that if I go from A to B, okay, when I say direction, maybe I go this way and then this way, okay? But the distance I covered is actually this one, okay? So this is what we mean by distance, and direction is the one that has arrows, something like that. But I will get back to that in a moment, okay? So let's move on with definitions for now. So the next one is the average speed, okay? Average speed, which is defined as the total distance covered over the total time. Okay, this is a scalar quantity because it's a speed. Okay, So let's move on. The next one we will talk about is the instantaneous speed. Instantaneous speed, okay, which is the speed at a particular instance in time, something like that. So particular instance, okay, and this is also a scalar, and we will also come back to this later because to understand it you need to talk about the motion graphs. So yeah, we'll come back to this later. But when I was talking earlier about the speedometer actually shows the instantaneous speed, okay? So it is what a car's speedometer shows, okay? Because think about driving, okay? Maybe you're driving with 60 kilometers per hour and then you press the gas and it accelerates to 70 kilometers per hour in another 2 seconds, okay? So in second 1 you were speeding with, in second 100, say, you were speeding with 60 kilometers per hour, and in second 62 you are speeding with 70 kilometers per hour. So something like that. The speed at that particular second is the instantaneous speed, okay? So that's that. Okay, now the next thing we will need to discuss motion and kinematics is acceleration, okay? And acceleration is the rate of change of velocity, pretty much, okay? So it's defined as change in velocity over change in time. So this can be written as delta v over delta t, which is equal to v minus u over t, okay? Where v is, we will, so this v is what we will use later when we discuss Suvat equations. So this is the final velocity and this is the initial velocity, okay? And this is the time elapsed between this change, okay? So acceleration is measured in meters per second squared, and it's a vector quantity, okay? If a is positive, then we have acceleration. If a is negative, we have deceleration, okay? Right, so let's see a few examples before moving on. And I have my 2 sets of notes in front of me just to make sure that I'm covering everything properly. So let's do a few examples, very simple examples, nothing fancy. Hopefully we will see fancier examples through the past papers we will go through. So let's say that I move from A to C through B, okay? And this is supposed to be a right triangle. I hope you see it. So let's say that this is 3 meters and this is 4 meters. This is the most famous right triangle in history because you know that the hypotenuse is 5, right? Okay. So this is the direction of the displacement, okay? So if I want to find the displacement between A and C, then we know that the displacement is the square root of 3 squared plus 4 squared, which is 5 meters. Okay, and the direction is northeast. Okay, maybe I should use a red color. So let's erase this and let's replace it with red. So that's the direction of the displacement. This is the magnitude of the displacement. Okay, so let's see another example. Let's say that I move from A to B, then to C, then to D, and then back to A. Okay, something like this. And let's say that this is 3 meters, 3 meters, 4 meters, and 4 meters. Okay, then the displacement in this case is simply 0. Okay, so because I started at A and I ended up at A. Okay, so the displacement is 0, but the distance covered is 14 meters. Okay, distance is 14 meters. Okay, because distance is a scalar. It tells you literally how far away, how much distance did I cover in my travel, which is 14 meters. But the displacement tells you how much you displaced yourself from the initial point that you started from. And in this case, we didn't displace ourselves at all, so 0. Okay, let's do one more. So let's say I start at D. Okay, I go back to C, then to B, and then back to A. Okay, so this is the same square as before. Okay, sorry, rectangle. So the displacement is now what? Can you guess? I started at D and I ended up at A. So the displacement is just 4 meters, okay? Because this is the displacement, okay? And the direction is the one denoted, okay? So direction is negative y. So direction is negative y, okay? And this is because displacement is a vector, remember? But the distance covered is 10 meters, okay? Because this is, let's see, this is 3 and 3 is 6 and 4, 10 meters, okay? So the distance covered is 10 meters, but the displacement is 4 because we started at D and ended up at A. And okay, we said that displacement is a vector and distance is a scalar. Let's see what else. Let me see what else I have here in my notes. Okay, let's see this example. From A to B, okay, so I'm gonna draw a line here to denote that this is a different concept. So let's say that I travel from A to B and my velocity, my speed is 100 meters per second. Okay, actually, no. I'm sorry, let me erase this. Let's say that this distance is 100 meters and I covered it in 10 seconds. And then I went from B to C. I covered 50 meters in 6 seconds. Okay, so VAB, the speed in the first segment, is 10 meters per second because I divide 100 by 10, which is 10. So that's my speed. But my velocity is also 10. So let's say plus 10 because we move in the positive x direction. Okay. Now from B to C, the speed is simply the distance over the time, so 8.33 meters per second, okay? But the velocity is also plus 8.33 meters per second, where plus denotes that we are moving in the plus y direction. But the average speed in this travel from A to C is the total distance, which is 100 plus 50 over the total time. So that's 9.38 meters per second. And you see that it's sort of like in between 8.33 and 10. Okay. Let me think. Okay, give me a second. Okay. Yes. Now let's although we are gonna see this through the motion graphs, let's see another example in which we do a 4-kilometer run. When I was a high school student, I used to do distance running, which I still do sometimes, but I am not into it as much as I was when I was younger. So from A to B, let's say I travel from A to B, the distance is 4 kilometers. So, and let's say I cover it in 27 minutes, okay? So here I am at some instance in time, and my speed is 3 meters per second. And then at another instance, I feel bolder and maybe I'm going downhill or something like that, and my speed is 3.5 meters per second. And then in this instance, a few moments later, I drop to 2 meters per second, okay? So all these things here, oops, I want to use a different color. So all these things here are what's called the instantaneous speed, okay? Instantaneous speed. So all these three instances, but my average speed is still just the 4 kilometers, which is 4,000 meters over 27 minutes times 60 seconds. So my average speed is 2.47 meters per second. So you see that this value is different than these instantaneous speeds, okay? All that matters to find the average speed is to know the total distance and the total time taken for that distance, okay? Okay, now motion graphs, okay, are very, very, very central to Unit 1 in the sense that they come up in past papers over and over and over again. So this is something you have to definitely know very well and know how to work with problems. Okay, of course, here we're going to talk about the theory first, and then hopefully I'm going to get into past papers soon once I'm done with the theory lectures in these videos. So what are motion graphs? They represent, okay, they represent how an object, oops, okay, how an object, let's write them all together, okay? So, how an object's distance or displacement or velocity or acceleration changes with time. So in that sense, there are only 4 motion graphs. I mean, there are more for those of you who are going to go study physics and such, but here in the A-level, the AS level actually, we will only study 4, okay? So displacement time, distance time, velocity time, and acceleration time, okay? And as a general remark, and we are going to get into details soon, there are gradients, okay, of this, the gradients actually, sorry, let's put it this way. The gradients or the areas, I'm losing my words here, I'm sorry. So the gradients of or the areas under these graphs, okay, as well as the shape of this graph, of these graphs, as well as the shapes of these graphs, tell you important information about the object's motion. The object's motion, okay? And let's jump in with the first such graph, which is distance-time graphs, okay? So let's name it A, and let's put a header there. So distance-time graphs, okay? So before we talk about them, recall that in a circular trip, not tip, trip, I'm sorry, in a circular trip, the distance the distance increases, okay? We don't need the always, okay? The distance increases, whereas the displacement is 0. And when I say circular, I really mean moving around a square, for example, okay? So I go from A to B, then to C, then to D, and then back to A, okay? A, B, C, D. Let's call this a rectangle, okay? So if I start at A and go all the way around, that's why I call it circular, and come back to A, the distance I covered is 8 meters, right? Because it's 4 sides times 2, that's 8, but the total displacement is 0. Okay, so for this reason, for this reason, the distance time graphs always increase. Okay, so let's write it like this. So this is the distance, and this is the time, distance and time. So let's make just a sample graph. So 100, 200. So distance is in meters and time is in seconds. So 100, 200, 300, and let's say 400. Okay, so in every interval we increase by 100 meters. Okay, let's move this up there so we have space for one more. Okay, 600. And then for the seconds, let's do 1, 2, 3, 4, 5, and 6. Okay, so a possible distance time graph might look like this. Okay, so maybe I go like this, and then maybe I go like this, and then maybe I go like this, and then like that. Okay, so the gradient is the instantaneous speed. Okay, so when we deal with these graphs, sorry. Okay, so the gradient of this graph tells you the speed. Okay, so for example, the gradient here, notice that the gradient is distance over time, which is the speed, right? And the gradient in this segment, so from here to here, say, is different from the segment that goes from here to here, okay? Because here the gradient is actually smaller, right? Yes, so yes, so this okay, the gradient here is again distance over time, so the velocity here is slower. Okay, this is what I'm trying to say. So okay, then from here to here the object moves much faster. Okay, so the gradient here is larger, okay? And we can see this because gradient is distance over time, right? So here we have a large distance and a small time, whereas here we have a small distance but a large time, okay? So the velocity here is slower. And by the way, when you work with gradients, it doesn't matter. I mean, you can take this to calculate the gradient, meaning that you can take this segment, or you can take this, or whatever, as far as you are on the same line, okay? But this applies to lines, like straight lines, okay? If you are dealing with something like this, and by the way, the instantaneous speed, let's see, so let's use red. So the instantaneous speed is the speed at a particular second, okay? Remember when we talked about it? So at second 3, okay, so this is the third second, the gradient is this one, okay? So because the speed is constant there, okay? So because you're dealing with a straight line, the gradient is constant, and the instantaneous speed at the third second is the same as the instantaneous speed at the second second, okay? But if you're dealing with a distance time graph that looks like this, so you have distance and time, and the distance changes like this with time, okay? So this is something that goes like t squared, parabola, okay? So let's say that they ask you to find the instantaneous speed at 4 seconds, okay? So maybe, okay, that's the 4 seconds, okay? And we don't care about the distance, so I'm not going to write anything. So how do you find the instantaneous speed at 4 seconds? So all you have to do is to draw a vertical line, okay, from the 4 seconds to the line that describes the distance versus time. I mean, okay, to the graph pretty much, okay, and take the tangent, okay. So you have to, that's the point, okay, and you have to get the tangent to that point, okay. So once you get the tangent, you have to find the gradient of this now straight line, okay. Okay, so let me write it here. So the speed at 4 seconds is equal to d over t. So this is the d. Actually, let's call it delta d to avoid confusion, okay? Because it's a change. It represents a change in distance. Delta d over delta t. Delta d, delta t. Okay. So that's how you find the speed at that particular second. Okay. And once you draw the tangent, by the way, it doesn't matter if you take the intervals I show here, or maybe you can use this, etc. As far as the line is straight, it doesn't matter which 2 points you select to calculate the gradient. Okay. All right. And before we stop talking about distance versus time graphs, let's draw one more. We already covered this, but just to be sure, so that's the distance time. Okay, so let's say that it looks like this. Okay, let's say that we have a sample that looks like this. Okay, so we know that here the object, the car, whatever this motion graph describes, it is moving slowly. Okay, so slow. Here it moves fast, okay, because the slope is steep, okay. Here it's not moving at all, it's stationary, okay, stationary, okay, which means that the gradient is 0. How do we know that it's stationary? Because the position doesn't change pretty much, okay. I mean, notice that from here to here, the object did not move at all. So 0 gradient, stationary object, okay. Here it moves fast again, and here it moves slow. Okay. And this is it as far as distance versus time graphs go. Now let's go discuss, let's call them B, the second case. Remember, it's 4 cases. So let's talk about the displacement time graphs. Okay. And now that you got a taste of a distance versus time graph, let's jump right in and draw an example. Okay, so let's have the displacement and the time. Okay, so a probable displacement time graph might look like this. Okay, okay, something like this, and then something like this, and then maybe something like this. Okay, so what's going on here? Okay, let's start with this part. Okay, this segment. Okay, this segment, in this segment you have the object moving forward. Okay, in this segment, the second one, the object is, it's the same case as this one we just discussed earlier. Okay, so the object is actually stationary because the displacement doesn't change. Okay, and the gradient is 0, which represents a 0 speed. 0 speed means something is not moving. Okay, now in this part of the graph we have a negative gradient. Okay, how do I know it's negative? Because okay, that's the gradient here is positive, but to calculate the gradient here you have to take okay, so this is your delta d, but your delta t is going to be negative. I mean, it has a negative slope. Okay, this is what I'm trying to say. Because sorry, you don't take a negative time. What am I saying? Sorry, I take that back. The reason why it's negative is because the final position is here and the initial position is here. Therefore, we subtract a smaller number from a larger number from a smaller number, which gives you a negative number. So gradient is negative, which means that the object is moving backward and fast. Okay, so backward and fast. How do I know it's fast? Because it's steep. Okay, whenever you have a steep slope in the distance or displacement graphs versus time, you know that the object is moving fast. Okay, in this segment from here to here, okay, the object is still moving backward, but it's slower. Okay, and then how do I know that? Because the slope is negative. Okay, and then it abruptly becomes the slope becomes positive again. Okay, this is not realistic. Maybe there should be a part here where it stops, maybe something like this and then like this, but I didn't do it that way anyway. So let's go to the graph we have at hand. So here the object moves forward now. Okay, forward, and it's kind of fast. I mean, it's kind of a steep slope, so let's call it fast. Okay, now the gradient of the graph for the, remember now this is the displacement versus time graph. Okay, so gradient is now the velocity, not the speed. Okay, because remember the velocity is also associated with a direction in space. Okay, that's why I say that here it's moving forward and here, for example, it's moving I mean here, oops, sorry, here it moves forward, but here it's moving backward. Okay, so for gradient is displacement over time and it's the velocity. Okay, and one more thing, the gradient at an instant is at a particular instance is the instantaneous velocity. Okay, so let me see, should we have an example? So yeah, maybe let me draw a small example. So I'm gonna call it S because S is displacement and time. Okay, so let's say that maybe from here to here I have a straight line, and then maybe I have something like this. Okay, and someone asks, what's the instantaneous velocity? Okay, this is 1 second, this is 2 seconds, okay, this is 1, 2, and then maybe 6. Okay, so in this segment over here, oops, how do we go back? Okay, in this segment, the instantaneous speed at 1 second is the same as the instantaneous speed at 2 seconds because this is a straight line. Okay, but for the instantaneous speed at 6 seconds, you have to draw the tangent again. Okay, this is gonna be a difficult tangent. Okay, but you can calculate it. Once you draw the tangent at 6 seconds, you can calculate, okay, maybe you can come here and here and calculate the instantaneous velocity, okay, which is positive, by the way. It's slow, but positive, okay? So, shall I write something down? I think it's self-explanatory, kind of, so I'm gonna move on. So, let me write down a few things that you need to keep in mind. Let me see, I'm also checking my notes. Again, I'm working with, through 2 sets of notes. So, yeah, okay. Okay, so, oops, let me use black. So, a positive gradient means a positive velocity, okay? And positive gradient looks like this, okay? Then a negative gradient means negative velocity, means that the object changes direction pretty much and it moves in the opposite direction, okay? A negative gradient looks like this, okay? Zero gradient, okay, means that the velocity is 0 and the object is stationary, and it will look like this, okay, straight line. Okay, it's not straight the way I drew it, but you get the idea. Okay, another thing you need to keep in mind is that the steeper the slope, the faster the velocity. Okay, and now the area under the curve has no physical significance. So when you deal with, and the same goes, by the way, for the area under the distance time curve, okay? So I'm gonna write it here, same as distance time graphs. Okay, so it means nothing. All right, let's go see an example. I will try to draw it, even though this is not the best place to draw things like this. Okay, maybe let me try the straight lines. Okay, no, this is not what I need. What I need is this one, and I need the black color. Do they have a black color? Do I get a black color? Okay. All right. So yes. So I need a graph. I need a line there, and I need a line down here. It's not straight. Okay. Let me try to do a better job. Okay. Good. Okay. Let me revert back to my pencil. Okay. So I have two axes. That's good. Let's call this S and let's call this T. Okay, I need to somehow have space for 40 meters. So 10, 20, 30, 40. Okay, that's good. Or maybe I can use 3 squares. So 10, 20, 30, 40. Okay, so I use three squares mean, so 3 squares mean 10 meters, okay? So, and that's the displacement in meters. And then time is in seconds. And I need 60 seconds, so I need 6 intervals. Let's take the spacing to be 3 squares again. Will that work? 10, 20, 30, 40, 50, and 60. Okay, so 10, 20, 30, 40, 50, 60. Okay, this is tedious. I'm sorry, guys. So, okay, so that's the 20 seconds. We have a straight line over there. Then from 20 to 30, we have a flat line. So the object there is stationary pretty much. Then we get a decrease to, so the object returns to 30 meters. Okay, something like this. Okay, then it's stationary again for 10 more seconds. Something like this. And then it goes to 0, but in a parabolic fashion. Okay, something like this. Now let's go calculate various things from this graph. So from 0 to 20 seconds, what's going on there? Let me check. We need to calculate the velocity. So the velocity is delta S over delta T. Since this is a straight line, we will use 40 over 20. So we will use the whole interval. So that's 40 and that's 20, right? So the speed there is 2 meters per second, okay? So I'm sorry. And the instantaneous velocity here or here or here or here is the same, okay? Constant speed. Velocity. Sorry. Now, from 20 to 30 seconds, okay, the velocity is delta S over delta T, but delta S is the same. It's pretty much 40 minus 40 over 10 seconds, so we get 0, okay? So you see that mathematically the slope is 0, okay, because we are dividing 0 with some time. Excuse me. So we get 0. The object is stationary. Now from 30 to 40 seconds, okay, we get the velocity is again constant. So let's use delta S over delta T. Now the delta S changed from 40 to 30, okay? So we have to subtract 30, a smaller number, from 40, a larger number, okay? And again, the time interval is 10 seconds, okay? So the speed there is minus 1 meter per second. But minus only means that the object changed direction, okay? So it's like a thing of, I don't know, a car moves from 0 to 40 meters, it stops, it waits for 10 seconds, and then it reverses and goes backwards to 30 meters. This is what's going on. Okay, then from 40 to 50, I don't need to try hard to convince you that the velocity is 0. I'm not going to do anything because it's a flat line, okay? And then from 50 to 60, we cannot talk about the velocity because the velocity is not constant, okay? This is a parabola, okay? So we can only talk about the instantaneous speed. So maybe in a paper, they might ask you, okay, what's the speed at 55 seconds? So somewhere there, okay? So if they ask you that, you have to take the gradient, take the tangent at 55 seconds and then calculate the gradient of that line, okay? And notice that the gradient is negative, meaning that the object is moving backwards still, but then eventually the gradient here becomes 0, which means it comes to a stop pretty much, okay? All right, so let me write this down. So V not constant, okay? But notice that the gradient is steep in the beginning and negative, okay? And it eventually becomes 0. So we have the acceleration pretty much. All right, so we covered the distance time graphs, displacement time graphs. Now let's move on to velocity time graphs, okay? So velocity time graphs. So they might look like this, so V and T. So maybe something like this. Actually, let me use a different color. It will help to see what's going on visually. So maybe something like this might be a velocity time graph, sorry. So something like this. Okay. So what's going on here? Okay, this is complicated. It looks complicated. So first of all, let me draw another thing over here. Okay. Okay. Let me think of how I want to talk about this. So the gradient of these graphs, okay, so the gradient shows the acceleration of the object. So pretty much in the flat lines over here, so from here to here, we have a flat line, and we have a flat line here, we have a flat line here, and another flat line here, okay? So here the object is moving with constant speed pretty much, which means that the acceleration is 0, okay? But here, it has a negative acceleration, which means that it decelerates, okay? And from this speed, from this initial speed up here, it goes to a 0 speed. So it comes to a stop pretty much, okay? Then it after some time, it starts again, but with a negative speed, which means simply that it moves in the opposite direction, okay? And it moves all the way to, and for some time period t, so this time period, I mean, it has the same speed, so constant speed. And then miraculously, okay, I don't know how this will occur in real life, but miraculously it turns around and it moves with a constant speed in the opposite direction. Okay, so this is this segment. All right, this was a lot of information, I think. Now, what about this area here that I drew, okay? I could have drawn an area here as well, but I didn't want to, so let's focus on that. So the area is proportional to velocity times time, which is also known as displacement. Okay, so the area under the curve tells you the displacement of the object. Okay, so for example, if you calculate this area, it will tell you the displacement of the object from here to here. Okay, if you calculate this area, it will tell you the displacement from this point to this point and so on. Okay, I drew some complicated graph in my notes. Let me try to decipher it and see what I'm trying to say. So what am I trying to say here? A, B, and then C. Okay, so let me draw another example, which will hopefully clear things out. So this is velocity and this is time. Okay, so This is point A, this is point B, then there is a point, okay. So A, B, this is point C, then we go all the way to D, and then we follow a straight line to E, and then we go to G, okay? So the velocity here is constant, and the acceleration is 0, okay? So from A to B, we have a constant speed motion. Then from B to C, okay, here is the 0, by the way, of the velocity, okay? So from B to C, we have V reducing, okay? So V reduces, therefore we have the acceleration, okay? And we know that because the gradient of the velocity time graphs is come on, what am I trying to say? Is the acceleration, right? So in this case, the gradient is negative, therefore it decelerates, okay? Until it comes to a stop at point at point C, right? The velocity is 0 there. But then what's going on? So now V increases, but in the opposite direction, okay? So despite the graph having a negative slope here, okay? So it appears as if this is an acceleration motion, but what is really going on is that the object is accelerating in the opposite direction, okay? So V increases, so from C to D, okay? From C to D, V increases, but in the opposite direction. And we can see this because we start from 0, and then the object has some large negative velocity at D, okay? So V increases in the opposite direction. I hope this makes sense. So we have acceleration, actually, as strange as it sounds. Okay, now from D to E, the object moves in the opposite direction because the velocity is still negative, okay? So from D to E, we have a constant velocity, but in the opposite direction, okay? And the acceleration is 0. And then what's going on here? From E, okay, I need the F, I need the point F there as well, okay? So from E to F, V reduces now, but because we have some large negative velocity, and then it gradually goes to 0. So V reduces, still moving in the opposite direction, okay? I'm gonna show that schematically in a moment. So V reduces in opposite direction. So we have deceleration. Okay, and then from F to G, that's a simple accelerated motion. So we have acceleration in the forward direction, in the sense that the velocity is positive, okay? So if you draw this motion, so from A to B, okay, the object has a constant speed. It then from B to C, so this is C. From B to C, the object decelerates until it comes to a stop at C. So at C, V equals 0. And then from C, it accelerates backwards, okay, to D. Then it moves to E, where it stops, okay. So at E, V equals 0. And then it moves now forward to point, actually it's forward, so I made a mistake in my notes. So from E, it moves forward to F, okay. Wait, what am I saying? I'm sorry. Okay, let's go back. Sorry. So from E to F, from E to F, what's going on there? We have from E to F, we have deceleration, okay, so negative acceleration, and then from f, at f the velocity is 0, it moves to g with a positive acceleration, okay, so that's the motion. Okay, it's a little bit involved, but I hope it makes sense. So for velocity time graphs, if the gradient is positive and the velocity is positive, okay, then we have acceleration, pretty much. Okay, so this will be, for example, this part over here, okay? Oops, I didn't want to delete it. Okay, so this part over here, the velocity is positive, gradient is positive, so we have acceleration. The second case is when the gradient is negative, okay, and the velocity is positive. In that case, we have deceleration. Oh God, this is complicated, I'm sorry. So we have deceleration. Okay, the other case is when we have a negative gradient and a negative velocity, okay, together, in which case we actually have acceleration. Oops, acceleration. And the final case is when the gradient of the velocity time graph is positive, but the velocity is negative. In that case, can you guess what we have? What kind of motion? We have deceleration. Okay, so when the signs are both of the same kind, we have acceleration pretty much. And when they are opposite, okay, we have deceleration, okay? So for example, okay, let's say I go to this segment over here, okay? The velocity is negative, the acceleration is negative. Therefore, we have acceleration, okay? Because remember, the object starts from 0 velocity and then it increases its velocity to this point over here pretty much, okay? So this will be your final velocity in the segment C from D. And this sounds confusing, I'm pretty sure, so it will make sense once we solve past papers. And in past papers, they will never give you something as complicated as what I'm showing here. So this is probably as bad as it can get, I think. Maybe I'm wrong, but this is my take. Now, the final one, and we will not spend almost any time on that, is the acceleration time. Acceleration time graphs. Okay, so let me draw an example. So acceleration and time. So maybe we'll have something like this. And then something like this, okay? All right, so what's important in these graphs is the area under the graph, okay? So the area, actually, let me erase this part here so I have space. So the area is proportional to acceleration times time, right? So what is that? It's delta V, because remember delta V is, acceleration is defined as delta V over delta T, okay? So if I multiply acceleration and time, I get delta V, okay? And the gradient of an acceleration versus time graph has no significance, at least for the A level, the AS level, okay? The AS-Level Physics. And don't laugh, I think, okay, before we say that, let me talk about one more thing I wanted to say. So if I take a random point on this acceleration versus time graph, the value of the acceleration at that particular time is the instantaneous. So the instantaneous acceleration. Okay. And I just remember that for the velocity time graphs, it's the same thing. Like if someone asks, what's the instantaneous speed at this second? Okay. You just read it off the graph. Okay. The instantaneous speed at let's say this is t0 and this is v0. So the instantaneous speed at t0 is v0. So you just read it off the graph, and you do the same in the acceleration versus time graphs. Okay, so that's the instantaneous acceleration. So if they ask you what's the instantaneous acceleration at t0, you just read it off the graph. So it's a0, for example. Okay, and the gradient has no significance, but for those of you who are gonna study engineering, probably aerospace engineering, mechanical engineering, or even physics, it comes up every now and then. This is not something you need for the AES level. I mean, I'm making a joke here, okay? The gradient of this graph is called jerk, okay? And let me show you actually. Okay, let me open my browser. So, gradient is what we are looking for. Gradient of acceleration versus, oops, time graphs. Let's see. So the gradient of an acceleration time graph represents the rate of change of acceleration, which is known as jerk. Okay, so I wasn't jerking. This is how it's called. But the rate of change of acceleration is not something that concerns high school students. Okay, it appears in the motion of aeroplanes, missiles, spaceships, those kind of things. Okay, so the acceleration is not constant. Okay, so it changes with time, and engineers need to know this kind of information when they design spacecrafts, for example, because they don't want to have jerk, as it's called. I'm not even joking. Because it creates friction, you lose energy, those kind of arguments, okay? But I didn't study engineering. I kind of went to an engineering school, but I didn't really study engineering. So, but I happen to know this kind of information because I don't know, I have an interest in technology, in case I never mentioned it before. And okay, this is a good time to stop this video because now that I'm looking into my notes, the next topics, I'm sorry, are mostly related to forces and such, so not really, I don't see, yes, I mean, it doesn't make sense to discuss forces right after discussing motion. So we are gonna stop here. Let me know how you find these videos, guys. I mean, if they are useful, if you have suggestions, if I make sense, so whatever, and I don't know, like, subscribe, and all these things, and see you in the next video.